guess it was last year maybe, I developed this little slide deck that we're just gonna look through really quickly. So there's not, Zach, we're starting class, dude. So this is just more of a kind of an overview thing before we get into the nitty gritty. So you don't really need to take notes on anything like this. It's also being recorded and all that kind of jazz. So let's, I think it's shared on Zoom and you guys can see it. Oh, I guess I could do that. If you shoot me an email to remind me, I'll do it, but I hadn't done it before. All right, so introduction to induction motors. Where's the damn slideshow button? Here we go. All right. So there are two major types of AC motors that we're going to be dealing with in this class. We have synchronous motors. We talked a little bit about synchronous motors towards the end of our lectures on electromechanical energy conversion. And the main characterizing thing about a synchronous motor is that the speed of the rotor, which I have here as NR, is equal to the speed at which the stator field is rotating. And we're going to talk a little bit here later on today about how we develop a rotating magnetic field in a three-phase system here in a couple minutes. Then there are asynchronous motors where the rotor speed is not equal to the stator speed. There is going to be a slight level of difference between those two speeds. We're going to talk about where they come from and why it's actually critically important. If we didn't have slip, an induction motor literally wouldn't turn. And we are going to focus our time on these asynchronous or induction motors first, okay? So in an induction motor, we've got this large kind of blown up image of what's going on. There are lots of different parts here, but the key features are the stator and the rotor, okay? So the stator is comprised of, I don't know if you can see my mouse or not. Can you guys see the mouse? No, not at all. Well, that's wonderful. Let me get up onto the screen and point it out then. So those well, I guess there's an arrow that says stator winding. So our stator is literally just a big electromagnet, okay? So that's just a whole bunch of windings. It's typically a three-phase winding. And it is stationary, so it's just housed inside this very large, usually a cast iron casing, which that casing is actually going to become part of the magnetic circuit as well. And then we have our rotor, which is located inside the stator windings. It is a cylindrical machine overall, so effectively the rotor fits inside of the stator so that there is a constant amount of air gap between the rotor and the stator so that we don't see any change in reluctance due to changes in the air gap overall. Then there's some other parts. Most of this stuff is literally just to house everything, but I do want you guys to notice that on the very back end of this guy, there is a little bit of a fan to try to cool things down. And then there's a case over it to allow airflow and also to keep you from getting your fingers cut off and all of that kind of stuff, because that fan is going to spin at the exact same speed as the rotor because it's all mechanically linked together. So the faster you run this guy, the faster the fan spins and the more it tries to cool itself down. All right. This guy right here would probably be a large one also because it has this eye bolt kind of built into it to allow you to pick it up and move it around, usually with some sort of mechanical suspension type device. So let's talk about where these guys are used, okay? So induction motors essentially are used literally everywhere. I would be willing to bet, well, the induction motor that's in that projector for the fan is probably a brushless DC motor, or it might be a very small brushed DC motor. So in this room specifically, I don't know if there is an induction motor, but I'd be willing to bet that we're feeling the effects of one because induction motors are used very regularly as components in HVAC systems, right? So we might see a very large three-phase induction motor on the HVAC unit for a building of this size, and then the compressor that's used as part of the refrigeration cycle is going to be a single-phase induction motor. we see, like I was just mentioning, we see induction motors literally everywhere. What's actually kind of interesting, you guys have probably heard about the war between Tesla and Edison, right? Over AC versus DC and all of that kind of good stuff, right? So Tesla was a huge proponent of AC power and all of that kind of stuff. And one of the reasons that he was such a huge proponent of AC power is because he helped develop the first AC induction motors. As a matter of fact, he had a deal with George Westinghouse where Westinghouse had to pay him, I think it was like $3 for every AC induction motor that was created. And effectively, Tesla was bankrupting the company that he was working for because there were so many AC motors going into production because they were used in so many things that he had to release Westinghouse from that deal. And that is one of the reasons, other than the fact that Tesla was also batshit insane in some ways, why he died effectively penniless. But the induction motor literally changed the industrialized world. Um, so it is one of the main reasons why we actually use AC power for distribution systems and all of that kind of stuff, is to be able to deliver power efficiently to large scale industrial induction motors. All right. So they're used literally everywhere. Let's talk about why they're used literally everywhere. To put it simply, they are rather simple machines. And they are incredibly durable because they don't have a whole hell of a lot of moving parts. They don't experience a lot of friction. So we have some induction motors over in Nethkin Hall that we were using in our power lab classes up until 2 or 3 years ago when we spent a considerable amount of money on new equipment. Those induction motors that we have over in Nethkin are from pre-World War II. They still work completely perfectly. So they have been essentially running for the better part of 70 years with no issues whatsoever. As long as you don't literally go in and start trying to like mess with the windings or physically try to damage them, they'll live through damn near anything. Okay. Because they are extremely durable, they are used a lot in hazardous environments. Because they are simple, they are relatively expensive. As I mentioned, they are effectively maintenance free. As long as you don't actively try to mess it up, it's just going to do what it needs to do. Excuse me. They have high efficiency. So at full load, we're seeing power factors of greater than 80% lagging, which is pretty good. And then another one that's very important is that induction motors are self-starting. So some types of motors or electrical motors essentially need a second starting circuit in order to get it to start spinning. You do not need that for an induction motor. It's able to generate enough starting torque to keep itself spinning once it spins up to speed. That being said, the principal disadvantages are that it has a relatively low starting torque. You guys probably might have experienced that before. I don't know if you've tried to like hold on to the rotor of a motor when it's spinning up. For certain types of motor, if you hold it at the beginning, it literally won't be able to do anything, and others it'll yank your arm.
Like what, it's oscillating fans?
Yeah. Yeah. They have very high inrush currents. So this is something that we're going to talk about a little bit later on. But essentially, right when an induction motor is starting, it effectively sees what are called locked rotor current. So because it's not spinning, the rotor windings effectively just look like a really large short circuit. And so we're going to see typically 6 to 7 times the amount of rated current is going to flow through those windings as it starts up. That literally lasts for just milliseconds. But if you don't design for that with your breakers and things like that, you can throw your breakers every time you try to turn one of these guys on. And then one of the principal disadvantages is that speed control is relatively difficult, although that can be completely mitigated by using variable frequency drives and all of that kind of good stuff. But simple speed control is incredibly difficult. Okay, so let's talk about the stator. So our stator is just a whole bunch of thin laminated sheets like we see here on the top right. They are effectively stacked together, and then those teeth have coils fed through them. And the coils are fed through radially around this guy. So there is like part of a coil on every one of these guys. The number of coils is going to be dependent on both the number of phases and the number of poles, and we'll talk about that a little bit more. But the speed of the stator field, NS, is given by 120 pi times F. So that is our X, or excuse me, 120 times F, where F is our excitation frequency. So here in the US, that might be 60 hertz. Over in Europe, it'll be 50 hertz. And then P is the number of poles. So essentially, if we have a 4-pole motor is going to spin more quickly than an 8-pole motor, et cetera, et cetera. So the number of poles that we have is going to cause our stator field to go down, or stator field speed to go down, which will in turn cause our rotor speed to also go down. So that's our stator. Just a big electromagnet, usually connected in a Y configuration.
Having more poles means a higher magnetic field.
So more poles are, it's more of a speed control type thing. And so this is what I was mentioning, it's hard to control their speed. So the stator field speed, NS here, effectively is controlling the rotor speed to some extent, meaning that the rotor speed is always trying to catch up to the stator field, but it'll never quite catch it, because if it does, all of our torque goes away, okay? So essentially, how this translates is if we have multiple poles on our machine, then our electrical frequency, let me draw a picture. This will be more helpful. So cancel that. So I'm just going to attempt to draw a shitty stator here really quickly, which is just going to be 2 concentric circles, right? So there's the outside. Here's the inner diameter. We're not going to worry about the rotor or anything like that. And you guys really don't need to necessarily be taking notes on this unless you particularly want to. I'm just trying to explain what's going on. So let's say that this was a 3-phase machine, okay? So we might have an A phase over here. So I'm going to do that in black. And I'm going to say that the current is flowing in on this guy, and it'll be flowing out on this guy. So this is our A phase, and we've got 2 poles, one positive polarity pole for our coil, the other one's the negative polarity pole. So positive is the one where the current's flowing out, negative is where the one's flowing in. Then we might have our B phase, so I'll do that guy in red over here. And our C phase would be over here. So this is a simple 3-phase, 2-pole stator system, okay? So this guy is going to spin, the rotor is going to spin at roughly 3,600 RPM. So 3,600 RPM, because it's going the full 2 pi radians, or 360 degrees. Hold on, think about this. So every time the signal here completes 1 cycle, the rotor is going to spin 1 full cycle as well, okay? If we had more poles, so let's say that I put So this is another pole for the A phase. This is another pole for the B phase. And this is another pole for the C phase, right? So now we have a 4-pole machine. So essentially, our rotor only has to travel half the distance it had before it sees the opposite polarity. And so it's going to spin slowly because of that. So the more number of poles we have, the less distance it has to travel before it sees that same phase of signal. That's why it spins more slowly. So poles are related to the speed at which it's spinning. Yes.
So would that also increase the torque by doing nothing?
I believe so. So let's look at that in a couple of minutes. We'll get into our torque and power relationships and all of that kind of good stuff here shortly. But torque is related to power and angular velocity, right? And I think is it torque is equal to power over angular velocity. Yes, so the slower we spin it, the more torque it'll develop. Absolutely right. That was a relationship that we talked about at the very beginning of our electromechanical energy conversion class when we were looking on the mechanical side of the thing, and we'll get into it again in an example problem at the very end of this class if we get that far. But yes, you're 100% right. Okay. So here's our stator construction. Now we're looking at our rotor. So there are two different types of rotors that we can see. Squirrel cage rotors are the overwhelming majority of the rotor styles that are used in induction machines. And we'll talk about why they're called squirrel cage in a minute, but it's literally just how they're constructed. It looks similar to like a cage you would keep a squirrel in. Then we have our slip ring rotors. So they have actual windings and all of that kind of stuff on them, whereas the squirrel cage rotor does not. Okay. So if we look at the squirrel cage rotor specifically, it's made of thin laminated sheets of metal. And then we hook metal bars up and they're organized to where the bars are very slightly oriented out of parallel. The purpose of orienting them slightly out of parallel like this is to help develop more torque. Okay. So the rotor consists of aluminum or copper bars that are welded together at their end ring. And then they have these guys just making them hold their shape and all of this kind of stuff. Like I said, oriented very slightly out of parallel. For a wound rotor, we have something more like this. So thin laminations with notches for actual windings. The rotor in a wound rotor has to have as many poles as the stator is. It is always wound for 3-phase, even if the stator isn't. It's still wound for 3-phase. The windings are connected in a Y configuration, and then they are connected to these slip rings. So the slip rings are the concentric rings that you see on the end of the shaft towards the bottom right-hand corner of the screen. And this is just where contacts are made to energize this guy. Okay. The slip rings, it says here, are connected to a Y-connected rheostat. Any of you guys know what a rheostat is? How many of you guys have heard of a potentiometer? A rheostat is just a 2-terminal variable resistor, whereas a potentiometer is a 3-terminal variable resistor. That's it. So you just don't have access to, if you don't use the third leg of a potentiometer, it's effectively operating as a rheostat. Okay. So fancy word for variable resistor. Okay. And you can change the resistance of those windings as part of how the rotor, or excuse me, part of how the motor starts. So you can increase the resistance to make it start more slowly and then gradually decrease the resistance to help it spin up to its speed. Okay, so these are the very, very basics of how they're constructed and all of that kind of good stuff. Now let's talk about how they actually wind up working. So the first several mini little topics that we're going to talk about here are all really conceptual and almost no math whatsoever.
Wow.
Lots of pictures. That is exactly right. All right. So let's talk about, cool your jets, guys. The development of rotating magnetic fields. So we're talking about this specifically right now. We're talking about induction motors, but this exact same principle is going to be the same thing for a synchronous motor. So this is related to what's going on in the stator. Okay. So I'm going to try to draw another little picture here. It's effectively just the same picture that I had a moment ago for what it's worth. So I'm drawing a stator with 3 phases, and I'm just going to label those phases. So here's my stator. This is going to be my A phase. So I'm just going to put a little note here that that's an A. And then this is going to be essentially the return path for my A phase coil. And so that's going to be A prime. So this A and A prime, these are the 2 poles for the A phase, and they represent essentially one coil. Okay. Then I'm going to have 120 degrees out of phase from this guy is going to be my B phase. So B is going to be over here. And then my B prime is going to be over here. And then C will be over here. And C prime will be right here. So this is a 3-phase, 2-pole stator winding. Okay. Each of these windings is going to carry a sinusoidally varying current. Okay. So if I were to plot my currents as a function of time, they might look something like this. So I'm just going to say from the jump that my A phase is going to have no phase angle. So that's going to just make this slightly easier for me to draw. Then this further. So here's just one cycle of what's going on in the A phase. So I'm going to do the black as IA of t, and this is just going to be Im cosine omega t. My B phase is going to be lagging this guy by 120 degrees. So it might start somewhere in the ballpark of here. So something like that, where this is IB as a function of time is Im cosine omega t minus 120 degrees amps. And then my C phase is going to be leading my A phase by 120 degrees. So it might look something like this. Where this is IC of t is equal to Im cosine omega t minus 240 degrees, or we could call that plus 120 degrees if we wanted to. So I'm going to label some specific points in time here. I'm also going to label some magnitudes. So this is Im down here. This is negative Im. This is going to be T naught. Then we're going to look right here at T1, right here at T2, right here at T3, and then here at T4 is when this cycle repeats itself. So for what it's worth, T0 is just when we're starting things up. T1 is when our A phase falls down to 0. T2 is when our A phase is at its negative maximum. T3 is when our A phase is back to 0. And T4 is when our A phase is at its positive maximum. And now to piss off Zach even more, I'm going to draw so many more little pictures as we look at snapshots of this thing in time. So this is what we've got going on. Okay, so we've got our stator, and it is energized because it has currents flowing into each of his windings. Okay, so at t is equal to the time I have labeled as t0, the value of the currents in each winding will be, so IA at T0 is just IM. So it's at its maximum value, okay? IB at T0 is going to be negative IM over 2, and IC at T0 is going to also be equal to negative Im over 2. So if I were to draw my stator, and actually, no, I'll draw it because you guys will get even more pissed off if I copy and paste and you guys don't get to.
I can.
So I'm trying to just redraw my stator winding here. For what it's worth, when I'm talking for each little step, you probably want to start with one of these drawings because we're going to look at it over and over and over again at different points in times. All right, so here's my A and A prime. Here's my B and B prime. Here's my C and C prime. So I'm going to start with my current in my A phase is positive right now. So I'm going to draw that representation as current flowing out of my A part and current flowing in to my A prime part. And so what I'm going to see if I use my right-hand rule here is essentially I'm treating my current as if it's flowing around in a coil like this. My thumb is giving me my direction of my magnetic field. And so it should be literally just perpendicular to this guy. So this is B for my A phase. I'll draw this arrow a little bit shorter so that hopefully we can see that's B for the A phase. Okay. Now for my blue or my B winding, I have a negative current flowing. So in the positive terminal, I'm going to put an X, and in the negative polarity terminal, I'm going to have a dot coming out. because the current is flowing in the opposite direction as what I had before. And so if I use my right-hand rule for this guy, I'm going to find that I should have a B field. It's going to be a little bit smaller, but it'll be in this direction. So this is B sub B. And very similarly in my C phase windings, I'm going to have a negative current. So that guy is going to have an X. This guy is going to have a dot. And that's going to wind up giving me BC like so. My net, damn it.
Yeah, it probably is just power source.
Just power, they told me that. And said, you know what, Dr. Harmon's gonna be in this class approximately this time, yeah, we gotta reset.
That's what I'm just getting. We're talking about power, so the power is a really.
Scared it.
After the brush was always talking about power, nobody's not on board.
I don't know. Okay, there we go. All right, so let's do a little bit of math here. Nothing wild or crazy. So our net magnetic field is going to wind up being what I'm going to call B max. So that's the contribution from the A phase. So our current is at its absolute maximum value that it will ever be, which means our B field is going to be as strong as it will be for that particular phase. And then my B phase is going to contribute 1/2 B max. Because my current is only half as strong. And then I'm going to have a cosine of 60 degrees here. And the cosine of 60 degrees is because I'm just trying to figure out which portions of all of my net magnetic field are adding together. So essentially, there's a 60-degree angle between this guy, and I'm only looking for the horizontal component because hopefully, pretty obviously, the vertical component of my B field in blue and the vertical component of my B field in red are going to cancel each other out because they're pointing in opposite directions. Does that seem reasonable? And then to this, I'm going to also add a 1/2 B max cosine negative 60. And this winds up coming out to be 3/2 times whatever my maximum field is going to be. And I'm going to put an arrow here to indicate the direction of the net field. So our net B field at this particular instant in time is 3/2 of what its maximum value for a single phase will ever generate, and it is oriented to the right. So now let's look at what's going on at T is equal to T1. So looking at our graph, at T1, our A phase current is literally just 0. Okay. Our B phase current, for what it's worth, is going to be the square root of 3 over 2 times IM. And the C phase current will be negative square root of 3 over 2 times IM. So if we once again look at what's going on with the field that's generated by our stator windings, there's our A phase. We're actually going to wind up just leaving both of those circles blank because there's no current. So no current's flowing in, no current's flowing out. So I'm just not going to designate anything there. for our B phase, this guy is positive, so it's going to get a dot. This guy over here is the opposite. And then for my C phase, because it's negative, this guy's going to get an X. And this guy's going to get a dot. We know that the A phase is going to generate no field whatsoever. So now let's look at what's going on with our B phase and our C phase. So using the right-hand rule, where we have currents flowing out in the bottom left-hand corner and flowing in the top right-hand corner, we're essentially going to get a B field that has this direction. So this is our B phase. And then the C phase is going to be something like this. Our net magnetic field in this case is going to be 0. That's our contribution from the A phase. √3/2 B max cosine 30 degrees. For what it's worth, the 30 degrees is the angle formed between this vertical axis and our field line. So we're just trying to figure out how much is in the up direction at this case. And then we're going to have plus √3/2 B max cosine of negative 30 degrees. And these guys wind up adding together to, once again, 3/2 B max. And now they're going to be in the up direction. So to kind of expedite things here really quickly, we could keep on going if we wanted to. So at that specific instant in time of t0, we have a net field with some specific value of 3/2 of B max directed to the right. We've fast forwarded in time, essentially 90 degrees, right? Or 90 degrees times, we fast forwarded an angle by 90 degrees, I guess would be a better way to put it. So now our net field is direction up, but it has that same value. So what did you guys think happened in between there? So Sam, you just did a little hand move. What did that hand move represent? A rotation. That's exactly right. That is exactly right. So our B field, as these currents are changing, is literally just rotating around our stator, and it's going to be rotating in a counterclockwise direction. So if we continued on at all of our other points in time, what we would actually see is that the magnitude of our B field is always constant, but its direction is just changing depending on where we're at in those cycles. That's only true for a three-phase induction motor, but essentially, if we have 3 coils that are physically located 120 degrees out of phase with each other, and we apply 3 currents that are 120 degrees out of phase with each other that have equal magnitudes, we are going to generate a constant magnetic field that rotates around at the exact same angular velocity as our excitation currents are flowing, right? So we are establishing a rotating magnetic field in our stator that's just spinning around and around and around as time progresses, okay? So I'm gonna skip ahead because we don't need to look at this over and over and over again. So summarizing, what we're gonna wind up getting, let me just draw the stator one last time. So here's our A, B and B prime, C and C prime, and we have some net magnetic field B net that is going to be spinning around with the exact same angular frequency omega that we are using to excite the coil with our currents. Okay, so that's all we're seeing here. So this is how we generate a rotating magnetic field, which is absolutely critical to both induction motors and synchronous machines. Okay. So are we good with this conceptual part? We have a reasonably good understanding of what's going on. So now let's talk about how this rotating magnetic field winds up generating a torque on our rotor. So we'll call this guy generation of torque. On the rotor. So I'm going to draw a very shitty cross section of a simplistic representation of a squirrel cage rotor here. Okay. So it's just going to be another picture. Sorry, Zach. So here's our end ring that we talked about previously. And our end ring is what is used to both mechanically and electrically connect the bars that form our squirrel cage rotor. So I'm going to put one conducting bar here, and I'm going to put another conducting bar here. So let me just put a note here that this guy is now representing a conducting bar. And let's say, for the sake of argument, that the field that is generated from my stator, so that's B sub S for my stator field, is starting out aligned with our conducting bars, and it'll be rotating around in this particular direction with some angular velocity omega. So what I have tried to depict here is that the two conducting bars connected to end rings on both sides effectively form a conductive loop, okay? So we essentially have another loop. So let's start by saying that the rotor is stationary, okay? So if the rotor is stationary, we can assume that as the magnetic field rotates, the flux passing through the loop formed by the rotor is going to change. So if we hold those two bars constant, like right now, as I have it drawn, essentially the flux passing through that loop is zero. If a little bit in time later, our B field is oriented orthogonal to our loop. So like we have here where it's perpendicular to the axis that our loop is on, then our flux is going to be at its maximum. Half a turn later, our flux is going to be at its maximum, but it's in the opposite direction. So we're seeing whenever it's literally in line with our bars, the flux is zero. It goes 90 degrees, our flux hits its maximum, 90 degrees more, our flux is zero, a further 90 degrees, and our flux is at its maximum, but it's in its opposite direction. That's the situation that I'm trying to describe here, okay? So Faraday's law of electromagnetic induction says that the conductors in presence of a changing flux will generate an induced voltage. So I'm going to write down a little mathematical equation here. So the induced voltage, that's E, will be equal to the cross product of what's called the relative velocity vector. And I'll talk about what that means in a minute. So crossed into our stator field, and then this product is dotted into L. So let me annotate this really quickly so that we can figure out what's going on here. So this is the relative velocity between the stator field BS and the rotor. So this is just the difference in speed of how quickly the stator field is moving minus how quickly the rotor is moving. So if the rotor is totally stationary, this relative velocity is at its absolute maximum. As our rotor starts spinning, that relative velocity gets smaller and smaller and smaller. Just as a conceptual question that is going to be pretty important here in a couple of minutes, what would happen? What would my relative velocity be if the rotor was spinning at the exact same speed as the stator field? It would be zero. If the relative velocity between the rotor's mechanical movement and the stator's field moving around is zero, what is my induced voltage? Zero. So if V relative is zero, then this whole thing has to go to zero. So essentially, if my rotor spins at the exact same speed as my stator field is spinning, I will not induce a voltage. As we'll see in a couple of moments, that's a problem, okay? Then I have this term L over here. This is literally just the length of the conducting bars, meaning that the longer I make those bars, generally speaking, the larger the voltage I'm going to induce. Okay, so the rotor bars and the end rings form a closed loop. The induced voltage is going to cause a current to flow. So let's figure out where that current is going to flow. That's pretty straightforward. So our current is going to flow through our conductive bars around the end ring, and that's just forming a closed loop, right? So if we had a situation to where, to draw my rotor again down here. So let's say, since I have a closed loop, I have some induced voltage, and this bars are going to have some amount of resistance, right? I should be expecting to see current is flowing literally through the bars in my rotor. So let's start from an assumption that current is flowing out of this bar into the end ring, and then it is flowing through the end ring into this bar to the other side, forming a closed loop, okay? So these dots here are representing the directions of current flow. So this is current flowing towards us, and this is current flowing away from us. And then once again, we have our B field, BS, that is rotating with some angular velocity, omega. Now, I've talked about this previously in the class before, but we'll recap it here. There is a phenomenon called the Lorentz force law, okay? So Lorentz force law states that F, this is effectively a magnetic force, is going to be equal to Q, that is a G, not a Q, my apologies, multiplied by V, which is the velocity of that charge moving crossed into my B field. And QV is the exact same thing as current I multiplied by our length. crossed into our B field, okay? So essentially, all this law says is that there will be a force generated on a current carrying conductor if that conductor is in the presence of an external magnetic field. And that is exactly the situation we have right now, right? We have these conducting bars that are carrying current into and out of the page. There is a magnetic field that is rotating around. And so I want us to figure out what direction those forces are acting on, right? And we're going to do that using the Lorentz force law. So let's start with the conductor where the current is flowing out, like so, okay? So our IL vector is directed out of the page towards us, right? Our current is flowing towards us, and so this is going to have the direction of current flow. And right now, our B field is directed straight up because that's our starting point. So if we use our right-hand rule, we would have my index finger is pointing in the direction, so it's out of the page. My B field is directed up, and so my thumb is giving me the direction of my force. So from what I'm seeing, with this coming out of the page, this going up the page, my thumb is pointing to the left. So my Lorentz force F is going to be acting to the left. So I'm going to draw a little arrow here. With an F like that. Okay. So that's the force that's acting on that particular conductor. Now, if we look at the conductor where the current is flowing into the page, so IL is flowing into the page, B is still in the up direction because it's always just in the up direction right now. So my current is flowing in. My B field is flowing up my page, and so my thumb is pointed in the right-hand direction. Sorry, I'm having to contort myself to show this to you all, but what I'm getting is a force that's acting direction to the right. So I want to ask you guys what I hope is a pretty simple question here. If my rotor is oriented to where it can spin freely, but it can't move left or right or anything like that, what happens when I pull on the top of it to the left and pull on the bottom of it to the right?
Stay right where it is. Stop.
It's going to start spinning. If I take a wheel and I spin like this,
Oh, you mean like,
Yes.
you said this.
look
You
at the
said like,
damn direction of the arrows.
yeah, it's gonna spin.
This is literally going to induce our rotor to start spinning. This is why we get a spinning rotor, because we have two forces that are effectively generating a torque, right? Torque is just force times distance, right? So we have these two forces that are pulling. So one is pulling the top to the left, the other one is pulling the bottom to the right, but they're affixed on a rotating pin. So this is just going to cause this guy to start spinning. So we're going to see that our rotor is going to follow the direction of omega, okay? Now, what's the limit on how fast the rotor can spin? Well, we know that the rotor, its absolute maximum speed that it could ever reach would be omega, right? We can't, if all we're supplying is an electric signal, essentially, that's oscillating at omega, we're never going to cause the rotor to ever spin faster than omega because we're not putting in any extra energy that will make that happen. If if our rotor spins at exactly omega, we have a problem because we no longer have any relative velocity, which means we're no longer inducing that voltage, which means we no longer have current flowing through our system. So essentially, we're always going to be just a little bit behind how quickly our stator field is spinning, okay? So let's see here. So our stator field, NS, this is the relationship from the slideshow, is going to be 120 times Fs, where this is the frequency of excitation of the stator windings, divided by P, which is our number of poles, right? So this is effectively the absolute maximum that could ever happen. NM, let me actually put another arrow here. So this is the stator speed, and NM is going to be the rotor speed. And it's got the subscript M because it's a mechanical speed, okay? So NM will always be less than or equal to NS, since VREL is equal to 0 for NM is equal to NS. And the difference of these two things is what we're going to call slip in just a moment. All right, so before we move on from this little miniature part here, how are you guys feeling about what we've talked about thus far? So we have, I believe, a relatively okay understanding of why we have a rotating magnetic field that's being generated by our stator. And then that rotating magnetic field is going to be acting on our rotor, and it is generating torque and causing this thing to spin, okay? So now let's talk about slip speed and slip. Am I good to start a new page, or you guys need a second?
Any question that's not exactly related to.
Sure.
There's a company that's talking at 11:30.
Mhm.
Is there any way we get out at 11:30?
Yes. I got no beef letting you guys out early for, let's call it professional development. Also, I would love 15 minutes to myself before I start advising. So I will happily grant your wish. All right, so slip speed and slip.
They're gonna be on.
Entergy will be here tomorrow evening.
Oh, are they?
Mhm.
Cause I just got a handshake from them, or just like a notification, that they have a spot in New Orleans for a relay engineer.
Yeah, Entergy, I know they're here for the career fair, and they're doing an IEEE industry talk tomorrow night, and I believe ISB 108 at, I think it's 6. I'm trying to remember, so it's Alex Marquardt. He's from, I think, around the Alexandria area. I don't remember exactly. And I think Ronnie Martin might be coming as well. He's from the West Monroe offices. And
So they got offices all around here.
oh, for sure. And then Aaron Hill may or may not be coming. I know him. He's the president of our Electrical Engineering Industry Advisory Board. He actually works on the generation side of things down in South Louisiana.
Okay.
So yeah, so they have offices all over. On one of the research projects that I'm working on with Entergy, it's working with people who are in offices out of Jackson, out of Little Rock, and out of New Orleans simultaneously. So yeah. Okay, slip speed and slip. Okay. So the slip speed of an induction motor is defined as the difference between the synchronous speed ns and the rotor speed nm. So n slip is equal to simply ns minus nm, excuse me. Okay. Fairly straightforward. So this is the speed. 99% of the time, though, we don't ever talk about slip speed. We just talk about slip as a quantity. Okay. So slip describes the relative motion of the rotor with respect to the stator. So our slip S is going to be ns minus nm over ns. So that's just the slip speed over the synchronous speed, or because slip speed and synchronous speed are related to, excuse me, synchronous speed and rotor speed are related to their respective angular velocities, we could also write this as omega s, which is just our angular excitation for our stator, minus omega m, the angular velocity at which our rotor is spinning, over omega s. So from here, we can manipulate this expression a little bit, okay? So we could say that the quantity ns minus nm, which is just our slip speed, is nothing more than our slip s times our synchronous speed. Okay? Rearranging this guy gives us nm is going to be equal to ns minus s times ns, or ns times 1 minus s. So I wanted to put it in this particular relationship so that we could see a couple of things, right? So this is one of the key relationships here, particularly nm is equal to ns times 1 minus s, okay? So from this relationship, if s is equal to 0, so if we don't have any slip, then we know that our rotor is spinning at the exact same speed as our stator field. Nm is equal to ns, okay? And again, talked about it a couple of times, that's generally considered bad for an induction motor because we're not generating any torque, okay? The second thing that we can infer is that if our slip is equal to 1, so if s is equal to 1, then nm must be equal to 0, which means our rotor isn't moving. Now let's talk about kind of ranges of things here, okay? So these are kind of two extremes. We have essentially what's describing for a synchronous motor where nm is equal to ns, and then we have a slip of essentially 100%, meaning that rotor isn't moving. Normally, we would see that our slip will be somewhere between 0 and 1. So if our slip is between 0 and 1, then the rotor is turning at a speed between ns and 0. And this is what we're going to call our normal operation, right? So we typically speaking want a slip. Usually it's somewhere between 3 to 5%. Can be a little bit more, can be a little bit less. It's going to depend on how much we load the motor and all of that kind of good stuff. But we're going to have some level of slip at all times if our rotor is spinning. All right. If S is greater than 1, so if our slip is greater than 1, then that means that NM is less than 0. So what do you guys think that that might mean?
Could be moving in the opposite direction.
It's exactly what it means. So it just means our rotor is spinning in the opposite direction of our stator field. Okay.
That's gonna be really.
So somebody said the key word there a moment ago, generator. So if we put mechanical energy on the rotor to force it to spin that way, effectively we're using this guy as a generator. That is what will happen. Okay. So let me just put rotor is spinning or turning opposite the stator field. And I'm just going to put a note down here. This can only, actually, sorry, I got a little bit mixed up, but we'll find out, I'll explain it in a second. This can only be true if external mechanical power is supplied to force the rotor to turn this way. And then I have a note here, the rotor will develop a braking torque that forces the motor to stop. So sorry, I made a little bit of a mistake a moment ago. Our fifth thing is if our slip is less than 0. So if our slip is less than 0, then our mechanical speed is greater than our synchronous speed. And this is how we get generator operation. So essentially, if we spin our rotor faster than the synchronous speed, we're generating power. If we spin it in the opposite direction, we are slowing the motor down or trying to turn it off. Sorry, I got those backwards. All right, let's look at one last little miniature topic here, and then we will be done for today. This one is very, very quick. Okay, so the last thing that I want to talk about is the electrical frequency of the rotor. This one isn't going to require its own full page. So essentially, what we're trying to figure out here is just if we have an AC signal generating our stator field, and then our rotor is not spinning quite as fast as our stator field is, what is the frequency of the current that is induced in our windings of the rotor? Or what's the frequency of the current that's flowing through our conductive bars and things like that? Okay. So essentially, if the rotor of an induction motor is spinning, the frequency of the induced currents and voltages in the rotor circuit will be different than the stator field frequency because of the relative velocity. Between the stator field and the rotor. So while running, the frequency of the induced voltages and currents is related to the slip speed as, I was going to have here, F sub 2. So this is the rotor electric frequency. And this is going to be simply the number of poles P times the slip speed N slip divided by 120. Now we can play with this a little bit. Okay. So we know that N slip is equal to S times NS from up here. Right? So N slip NS minus NM is equal to this S times NS. So I'm just going to substitute in that relationship. So we'd have P times S NS over 120. Now we know that NS, if we go back here, is 120 times our stator frequency over P. So I can substitute that in. So that looks like P over 120 times S. Then I have my stator frequency, which was 120 F stator over P. Looking at this guy, we literally just get this 120 cancels this 20, this P cancels this P, and the electric frequency of our rotor is literally just the slip times the frequency of our stator. Yeah, F2, so the rotor electric frequency is equal to slip, so let me just put a note here. And this Fs is stator frequency. All right. That is a good stopping point for right now because I don't think we have enough time to get through the example before you guys wanted to duck out for that little PD thing. So we'll start our next class meeting off with an example of how to use some of these relationships to do things with it. Okay, so we have a relatively okay-ish idea, I think, of what control, like what parts the induction motor is made of, why it's behaving the way that it's behaving. We'll get into application and all that stuff here in a moment. Yes, sir.